Now we are going to talk about another method to identify the topology, that is the Willson loop method. With this method, we will have a deeper understanding about this bulk boundary correspondence. Let's start again from a two-dimensional insulator. And this insulator here, we plot the band structure in this kx, ky plane. We know if we cut a line along ky here, it's also an insulator, but it's one-dimensional. If we integrate the block wave function along this line, for this quantity, actually this is the Berry surface. It's corresponding to the one-year charge center of the valence band. Here, because theta is the one-year charge center, is corresponding to the inner coordinate of the valence band wave function. And here you see it's also a wave function of kx, because at different kx, this insulator cut, this line are different. Now let's plot theta as a function of kx. And we will see the one-year charge center at different kx are slightly different. It has an evolution. Because it's periodic, it repeats along the y-axis between 0 and 1, and to higher, to 2, 3. It is also periodic along kx. And therefore, if we start from minus 0.5, the boundary of the Bernoulli zone, to another boundary, it will recover itself. Therefore, from the left end to the right end, this line, this evolution, should be a smooth evolution. But there's only two ways to connect them for a two-band model. One way is this 0 connect to another 0 smoothly. The second possibility is from this part of the periodicity connect to this one, or opposite, or from this 0 to another 1. Clearly, we see there's a difference of topology. And since this is periodic, for example, along the y-axis, if we roll this periodic boundary condition into a cylinder, we see it better. You see here along kx, this cylinder, then the first one is topologically different from the second one, because the second one has a winding around the cylinder. Clearly see they are topologically different. But how this topology, how it's connected to the boundary? Yeah, we always talk about this bulk boundary correspondence. Let's look at it. Suppose this is the one-year center evolution, and it's exactly the same one for the right one. We call it chain number 1. Later we will understand why it's chain number 1. Here, in this case, the evolution is here. Every yellow box is the periodicity along y direction. And if we look at the real space, suppose we have an electron travel along kx from right to the left. Then the consequences is also shift along the y-axis, right? It will shift, like one shift to another unit cell, the second unit cell to higher, higher, higher. Then the consequences, you see immediately. If we have a boundary, this electron has nowhere to go. Here we have accumulated 2 electrons, but at this boundary, there's no electron left. Here we call it charge pumping. And the charge pumping is directly the consequence of this one-year charge center evolution. And it also tells us on the boundary, we will have some special boundary states, different from bulk. And yeah, this evolution, usually also called this Willson loop evolution if we have many bands. This evolution can be more complicated, but its general feature is the boundary will become very different from the bulk. And one more feature you will see is actually the pattern of this evolution will be exactly the surface state, the boundary state dispersion. Now let's go back to the same band structure. And this one, the evolution, this is the trivial case. That one corresponding to we have a winding case. This winding case, you see, if we go to calculate really a boundary state, the edge state, that is, here is exactly that one. This is the edge dispersion. This is the insulator, the bulk states, but inside the bulk gap, we have a chiral edge. This chiral edge means here, the electron only move to one direction. And more important, what you see is the Willson loop shape is topologically identical to the edge state dispersion. And this is the case for a chain insulator, but if we have a topological insulator, like this Z2 number, then actually why it's called Z2 number? Because here we have only 2 possibilities for the topological insulator. And we said this mu0 either 0 or 1, right? Or in the Willson loop language, here it tells us if we have time Wilson symmetry, this time Wilson invariant point kx0 or the zone boundary, we have time Wilson symmetry, it always have this Kramer's degeneracy, this double degeneracy. Because the valence band is double degenerate, its one-year charge center also double degenerate. This is the basic requirement. Like from this point to the middle, there are two double degenerate one-year center. Now let's connect them. A trivial way to connect them is these two stars, they meet again in the middle. And there's another possibility is these two, they split. They meet with another partner. In this sense, between two time Wilson invariant points, this Kramer's partner, they just switch to each other. And this switch gives us a topological change. And you see the edge states, actually the edge states has exactly the same shape as this one-year center. And please remember the edge states is a direct calculation with the edge structure. Here, this topological invariant, this Willson loop, just a calculation from the bulk band structure is from this bulk, not that edge. In this sense, we understand the boundary. We know how the bulk evolve. We know the bulk topology. We will know there will be a special surface state. We even know how the surface state dispersion looks like. Let's go to a more realistic material. Actually, this is a band structure of bismuth selenide. This is a bulk band structure. If we massage this band structure or re-understand this band structure from the viewpoint of the Willson loop, the one-year charge center, this is what we get the Willson loop for all the valence band. Because we have many valence band, therefore we have many, you see many dispersions in this Willson loop. This Willson loop evolution, you see exactly, you see the Dirac coin. You see the clear Dirac coin. On the surface, there are Dirac coin too. And this is a very beautiful example of this bulk boundary correspondence. Now we know this Willson loop method. Simply from the bulk band structure, we get this Willson loop. Or in other words, Willson loop include the message of the wave function, give us a different angle to look at the band structure. We know immediately the topology. Not only the bulk topology, also we know immediately how the surface state disperse. And so far, everything is prepared. We know the DFT method, how to calculate the band structure. We know the band inversion, parity, and the Willson loop. Then how to identify the topology. In the next lectures, we will go to the realistic materials for topological insulator, topological semi metals, and then there we investigate the real material.